So today we're going to be solving October-November 2022 paper 21. Question number 1 says, atoms with nuclei containing an odd number of protons tend to have fewer isotopes than those with an even number of protons. Gallium has two stable isotopes, gallium-69, gallium-71. Complete table 1.1 to show the numbers of protons, neutrons, and electrons in the two stable isotopes of gallium. So if we look at the periodic table, gallium has the atomic number 31, right? It's in group 13, atomic number 31. So gallium has atomic number 31, that's the proton number, right? So there's 31 protons. It's a neutral atom, so it has the same number of electrons. And the nucleon number for gallium-69 is protons plus neutrons, right? So if we have 31 protons, we have 69 minus 31, that is 38 neutrons. Okay, for gallium-71, same number of protons and same number of electrons, right? Because they're isotopes, but a different number of neutrons. Here we have 40. Okay, 71 minus 31. Define relative atomic mass. The relative atomic mass is the weighted average. It's the weighted average mass. The weighted average mass of all the naturally occurring isotopes. Of all the naturally occurring isotopes of an element relative to 1/12 the mass of an atom of carbon-12. Relative to 1/12 the mass of an atom of carbon-12. Okay, that's the carbon-12 isotope, an atom of carbon-12. The relative atomic mass of gallium is 69.723. The relative isotopic masses of gallium-69 and gallium-79 are given. Use this information to calculate the percentage abundance of gallium-69 elemental gallium. Show your working. Assume that the element only contains these two isotopes. Give your answer to 4 significant figures. So over here, we don't know the abundances of either of these two isotopes. Okay, we want to find the abundance of gallium-69, the percentage abundance. So let's say that the percentage abundance of gallium-69 is X%. Now, since we only have these two isotopes, the total abundance of these two is 100%. If this is X%, then this would be 100 minus X%, right? This would be 100 minus X%. Now, if we had a total of 100 atoms, X of them would be this guy, and then 100 minus X would be this guy over here. So we can say that the total mass of those 100 atoms, right, would be X times 68.926 plus 100 minus X times 70.925 divided by the total number of atoms. So that would be 100%. Again, if we had a total of 100 atoms, the total mass would be X times 68.926 plus 100 minus X atoms of this guy times 70.925. So then the average mass would be this total mass divided by 100. So that's the relative atomic mass, which is given to us as 69.723 is equal to 68.926x plus 70.925 times 100 is 7092.5. 7092.5 minus 70.925x divided by 100. Let's just multiply 100 on both sides. So we get 100 times 69.723 is equal to this. We just have to solve for x. So here if we solve for x, we get x is equal to 60.13%. Okay, to 4 significant figures. So that's 1, 2, 3, and then 4. Okay, so x is equal to 60.13%. Right, that's the percentage abundance of gallium-69. Okay, doesn't matter which one of these two we set as x and 100 minus x. Okay, we just want to find the abundance of gallium-69. That's why I chose to set that as x, and then the other one would be 100 minus x. Another thing to keep in mind is that we do not use the mass numbers. Okay, the mass numbers are integers, whereas the relative isotopic masses are experimentally determined. Okay, if these isotopic masses aren't given, only then we use the mass numbers. So in this case, since the isotopic masses are given, we're going to use these in our calculation. Potassium also has two stable isotopes. Both isotopes have the same chemical properties. Explain why both isotopes of potassium have the same chemical properties. The chemical properties are determined by the electronic configuration. Okay, now since we have two different isotopes, right, they have the same number of protons, same number of electrons, they have the exact same electronic configuration. The only thing that differs is the number of neutrons. So they have different physical properties, but the same chemical properties because they have the same electronic configuration. Okay, they have the same electron arrangement or the same electronic configuration. State the full electronic configuration of an atom of potassium. Again, we can take a look at the periodic table over here. Now, potassium is in group 1, right? Group 1 is the first column in the S block, so it ends with 4s1. It ends with 4s1. It's in the fourth period, so 4, and it's in group 1, so it ends with s1, 4s1. So we have 1s2, 2s2, 2p6, 3s2, 3p6, that's argon, and then 4s1. Okay, so the electronic configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. The first, second, and third ionization energies of potassium are 418, 3070, and 4600 kilojoules per mole, respectively. Use this information to explain why potassium is in group 1. Now, since potassium is in group 1, right, it only has one valence electron. Right? It has a total of 4 shells, and there's only one valence electron. So the first electron is relatively easy to remove. And then the second electron and the third electron will be removed from the third shell. The first electron removed is from the fourth shell, and then the next two are being removed from the third shell. So you see a big jump from the first to the second ionization energy. The first electron is removed relatively easily, whereas the second and the third one are much more difficult to remove. Okay, so what we can say over here is that there is a big increase. Okay, there is a big increase. Okay, or jump. There's a big increase or jump from the first to the second ionization energy, which suggests that therefore there is only one valence electron, right? The second and the third electrons are removed from a shell closer to the nucleus. Right? Hence, there's only one valence electron. Okay, hence there is only one valence electron. If there's only one valence electron, it's in group 1. So here we have question number 2, which says magnesium shows reactions typical of a group 2 metal. Part A says draw a labeled diagram to show the bonding in magnesium metal. Now, since magnesium is a metal, right, it has metallic bonds. Now, metallic bonds are electrostatic forces of attraction between cations and a sea of delocalized electrons. So we have to draw a diagram showing metallic bonding, right? So we have cations, right, of the metal. You don't have to show the charge on the cation, right? You can just show the positive over here doesn't indicate the actual charge, it indicates the fact there are cations. Okay, so there are cations, and then we have a sea of delocalized electrons. Okay, we have a sea of delocalized electrons like this. So we have to label this. We have cations. Okay, and then we have the sea of delocalized electrons. Part B says figure 2.1 shows some reactions of magnesium and its compounds. Identify the other products of reactions 1 and 2. So magnesium is a reactive metal. When it reacts with HCl aqueous, that's hydrochloric acid. When it reacts with acid, we form salt and hydrogen gas. Okay, so the other product here is hydrogen gas. Okay, you can identify that by name or by the formula H2. And then for reaction 2, we have magnesium carbonate, which is a basic solid reacting with HCl aqueous. Right, again, hydrochloric acid is reacting with metal carbonate, so we get salt, magnesium chloride, and carbon dioxide and water. So the other products that we have here are carbon dioxide, okay, and water. Okay, you can give the formula as well, so CO2 and water, which is H2O. Reaction 3 is used to form a precipitate of magnesium hydroxide from magnesium chloride. State why calcium hydroxide would not form a precipitate of barium hydroxide from barium chloride. So in reaction 3, what they're doing is they're reacting calcium hydroxide with magnesium chloride. Okay, we have a solution of calcium hydroxide, and what ends up happening is that the precipitate of magnesium hydroxide ends up forming. The question is saying, why can't we do the same thing with barium chloride? Why don't we get a precipitate of barium hydroxide? Now, when we talk about hydroxide solubility, okay, it increases down the group. Okay, it increases down the group. So magnesium hydroxide is less soluble than calcium hydroxide because calcium is lower down the group, the hydroxide is more soluble. So what happens is that the hydroxide ions over here, they precipitate, okay, they form a precipitate with magnesium of magnesium hydroxide. It doesn't work with barium over here because barium hydroxide is more soluble than calcium hydroxide, so you wouldn't get a precipitate, okay, because barium hydroxide is fairly soluble, okay, it's very soluble, so you don't get a precipitate. So this wouldn't work with barium chloride the same way, okay, this wouldn't work the same way with barium as it does with magnesium. The reason why is because barium hydroxide is soluble, okay, is more soluble than calcium hydroxide, okay, so it's soluble in aqueous solution, okay, or specifically it's more soluble than calcium hydroxide as well, okay, and the reason why is because the solubility of the group 2 hydroxides, okay, the solubility of the group 2 hydroxides increases down the group. Increases down the group. State the type of reaction that occurs in reaction 4. So in reaction 4, magnesium carbonate is being heated to form magnesium oxide. This reaction over here is a thermal decomposition reaction. Okay, magnesium carbonate is being decomposed to form magnesium oxide and carbon dioxide. Okay, the type of reaction here is thermal decomposition. One centimeter cube of magnesium chloride is placed in a test tube. A few drops of silver nitrate are added, followed by 1 cm cube of dilute aqueous ammonia. State in full what is observed in this experiment. So initially what happens is when the silver nitrate is added, okay, the silver ions form a precipitate with the chloride ions. Okay, the silver ions form a precipitate with the chloride ions of silver chloride. Okay, so the first thing that we observe is that a white precipitate forms. Okay, white precipitate forms of silver chloride. Okay, that's Ag plus Cl minus. Okay, and then silver chloride dissolves in aqueous ammonia. Okay, in dilute aqueous ammonia. When we add aqueous ammonia, the white precipitate dissolves. So we say white precipitate forms, which then dissolves in the dilute NH3 aqueous. When 1 centimeter cube of magnesium chloride is added to 1 centimeter cube of bromine aqueous in a test tube, the solution remains orange. Explain this observation. So over here we have no reaction taking place. So the solution remains orange means that the bromine doesn't react. Okay. Now we should know that when we go down the group, right, for the halogens, Cl, Br, and then I, right? Down the group, the oxidizing strength of the halogens, okay, the oxidizing strength of the halogens, those are the diatomics, right? The oxidizing strength decreases. Okay, the oxidizing strength decreases, right? So chlorine is the strongest of the three oxidizing agents here, and iodine is the weakest. And for the halide, it's the opposite. For the halides, it's the opposite, right? The reducing strength of the halides increases. Reducing strength increases. Okay. Now here what we have is we have bromine trying to react with chloride. Now since bromine is a weaker oxidizing agent than chlorine, and chloride is a weaker reducing agent than bromide, okay, bromine doesn't want to gain electrons as much as chlorine does. So chlorine wants to remain in its ionic form more. Since bromine is a weaker oxidizing agent, okay, it will not be able to oxidize chloride. Conversely, since chloride is a weaker reducing agent than bromide, chloride will not be able to reduce bromine. So what we can say over here is that there's no reaction because bromine, okay, bromine is a weaker oxidizing agent. Bromine is a weaker oxidizing agent than chlorine and is unable to oxidize the chloride ions. Okay, it's unable to oxidize Cl minus. Here we have question number 3, which says some of the common chlorides of period 3 elements are shown in the list. From this list, identify all the chlorides that have giant ionic structures in the solid state. So sodium chloride and magnesium chloride, okay, have giant ionic structures. They're ionic compounds. So NaCl and MgCl2. Okay, aluminum chloride, if you guys remember, right, is sort of like a mixture between ionic and covalent, right? So we treat it as a covalent compound. Okay, we treat it as a covalent compound in our syllabus. So it's sodium chloride and magnesium chloride. All the chlorides that react vigorously with water to form strongly acidic solutions. So all the covalent chlorides, aluminum chloride, silicon tetrachloride, and phosphorus 5 chloride or pentachloride, okay, all three of these form strongly acidic solutions. The reason why is because they have covalent bonds, okay, because they have covalent bonds, right, these bonds can be hydrolyzed, okay, these bonds can be hydrolyzed, okay, by water. And when these bonds are hydrolyzed, it results in the formation of an acidic solution. Because these guys react with water, okay, because these guys react with water, that results in the formation of an acidic solution. So all three of them, okay, AlCl3, SiCl4, and PCl5. The chloride that dissolves in water to form a neutral solution. Sodium chloride is the chloride that dissolves in water to form a neutral solution. Okay, the single chloride. Okay, when it says the chloride, we're talking about only one chloride over here. Now, magnesium chloride, we do say sometimes that it forms a neutral solution, but the solution is very, very slightly acidic. Okay, it's just slightly below 7, the pH. So it's very slightly acidic. So sometimes we do say it's neutral or almost neutral. However, sodium chloride, okay, forms a neutral solution. The pH of the solution is 7. The next part says the chloride formed from the element with the highest melting point. So in period 3, right, which element has the highest melting point? And we know that that is silicon, right? Silicon has a giant covalent structure, right, where the silicon atoms are tetrahedrally bonded to 4 other silicon atoms in a macromolecule, right, similar to diamonds. Structure is very similar to diamonds. So this element, silicon, has the highest melting point. So that's the element with the highest melting point. So the chloride formed from that element is just silicon tetrachloride. Okay, so the answer is SiCl4. The chloride formed from silicon, okay, the element with the highest melting point. Part B says NaCl, sodium chloride, is one product of the reaction of chlorine gas and cold aqueous sodium hydroxide. Identify the other products. When chlorine reacts with cold aqueous sodium hydroxide, okay, NaOH aqueous, we get sodium chloride, and then we also get NaClO, which is sodium chlorate 1 and H2O. Okay, this is a disproportionation reaction because the chlorine is being oxidized and reduced. Okay, it's being reduced from 0 to -1 and it's being oxidized from 0 to +1. Okay, it's being reduced from 0 to -1, it's being oxidized from 0 to +1. Okay, so the other two products here are sodium chlorate 1 and water. Okay, so NaClO. So you can give the name also, sodium chlorate 1 and H2O. PCl5 reacts with alcohols to form chloroalkanes. Identify this type of reaction. So when alcohols are converted to chloroalkanes, right, the Cl substitutes for the OH group. Okay, so this is a substitution reaction, and specifically it's a nucleophilic substitution reaction. Okay, so this is a substitution, or you can say nucleophilic substitution reaction. Draw the structure of the organic product formed in the reaction of an excess of PCl5 with butane 1,3-diol. So butane 1,3-diol, right? Butane 1,3-diol is this guy over here, right? We have an OH group on carbon number 1. We have an OH group on carbon number 1, and we have an OH group on carbon number 3, right? We have an OH group on carbon number 3. And when this guy reacts with an excess of PCl5, both the OH groups are substituted by a chlorine atom. Okay, both the OH groups are substituted by a chlorine atom. So we end up getting 1,3-dichlorobutane. Okay, 1,3-dichlorobutane. So that's the structure of the product. Sulfur S8 reacts with chlorine to form several different chlorides. The most common are S2Cl2 and SCl2. SCl2 forms when sulfur reacts with an excess of chlorine. SCl2 is a cherry red liquid that reacts vigorously with water to form an acidic solution. Use this information to deduce the bonding and structure shown by SCl2. Explain your answer. Now, SCl2 is a liquid at room temperature, okay, which suggests that it's a simple molecular compound or a simple covalent compound, and it reacts vigorously with water to form an acidic solution. That's similar to how AlCl3, SiCl4, and PCl5 behave, right? Those are the chlorides that form acidic solutions. Those are the period 3 chlorides that form acidic solutions with water, okay? So similarly, SCl2 does the same, and the reason they form acidic solutions is because you have covalent bonds which can be hydrolyzed. So the bonding here is covalent and the structure is simple molecular or simple covalent, okay, because it's a liquid at room temperature. So it has a relatively low melting point. So we can say that it has a simple molecular structure, okay, simple molecular structure, right, because it has a low melting point, right? Again, that's suggested by the fact that it's a liquid at room temperature, right? That's given to us in the question. With covalent bonds, right? So the bonding is covalent, so it's a simple covalent or a simple molecular structure, right? And we know that it has covalent bonds which can be hydrolyzed by water, okay, which can be hydrolyzed by water, and that's why it forms an acidic solution, because it can react with water. Calculate the enthalpy change of formation of SCl2. You may find it useful to use Hess's law to construct an energy cycle. So firstly, when we talk about the enthalpy change of formation, right, that's the enthalpy change when 1 mole of SCl2, is formed, in other words, it's the product, right, from its constituent elements, in their standard states, okay? So here we're going to say sulfur is S8 because that's what they've given us in the question, right? Sometimes we do write sulfur as S as well, okay, but here we're going to say S8, and then we have Cl2. And then again, when we talk about the enthalpy change of formation, we have 1 mole of this guy being formed, 1 mole of the product here, okay? So the right hand side has to be 1. So then we have 1 Cl2 and we have 1 over 8 S8. Again, this is the enthalpy change we want to find, okay? That's the enthalpy change of formation we want to find. We can complete this energy cycle using the reactions that they've given us above. Now, if you look at the reactions over here, right, they've shown us the reaction of sulfur and chlorine to form S2Cl2, and they've given us the reaction of S2Cl2 with chlorine to form SCl2. Right? We want to find the enthalpy change of formation of SCl2, right? The only thing missing in this energy cycle is S2Cl2. Okay, so we can write that down, right? We have S2Cl2 over here, and 1 mole of S2Cl2 can react with chlorine to form 2 moles of SCl2. 1 mole of S2Cl2 can react with chlorine to form 2 moles of SCl2. We were forming just 1 mole of SCl2, so we have 1 over 2 S2Cl2. Okay, so we can first draw an arrow from S2Cl2 to SCl2, right? This arrow over here, and this enthalpy change has a value of negative 20.3. Okay, negative 20.3. Again, because when S2Cl2 reacts with chlorine to form 2 SCl2, it's negative 40.6. That's for 2 moles of SCl2. Here we have 1 mole, so that'll be minus 40.6 divided by 2, so that's minus 20.3. The other arrow that we can draw is by looking at the first reaction, right? That's the reaction from the elements to S2Cl2. That's the reaction from the elements to S2Cl2. Now, for 4 moles of S2Cl2, the enthalpy change is negative 58.2. So then for half a mole of S2Cl2, what would that be? So if for the formation of 4 moles of S2Cl2, it's minus 58.2. For 1 mole, it would be minus 58.2 divided by 4. For half a mole, it would be minus 58.2 divided by 8. Okay. For 1 mole, it would be divided by 4. For half a mole, it would be divided by 8. So we have minus 58.2 divided by 8, right, which is minus 7.275. Okay, so minus 7.3. Okay, minus 7.3. So this arrow is minus 7.3. So again, in this energy cycle, what we're saying over here is that the energy change, the enthalpy change of formation, right, when the elements are converted to SCl2 is the same as the elements being first converted to S2Cl2 and then S2Cl2 being converted to SCl2, right? So then the enthalpy change of formation over here, right, the enthalpy change of formation, that's the direct route, right, from the elements to SCl2 is equal to minus 7.3 plus minus 20.3. Okay. The enthalpy change of formation is minus 7.3 minus 20.3. So we get negative 27.6 kilojoules per mole. So that's our answer. Okay, negative 27.6 kilojoules per mole. State the effect of a decrease in pressure to the position of equilibrium in reaction 2. Explain your answer. So if we go to reaction 2, okay, if we decrease the pressure, what happens to the position of the equilibrium in reaction 2? Okay, now when we talk about pressure, right, changes in pressure affect the position of the equilibrium only when gases are present. Okay, an increase in pressure favors the side with fewer gas molecules or fewer moles of gas. So a decrease in pressure favors the side with more moles of gas. Now if you look at reaction 2, there's more moles of gas on the left hand side. There's more moles of gas on the left hand side, right? There's 1 mole of gas over here and 0 moles of gas on the right. So again, increase in pressure favors fewer moles of gas, decrease in pressure favors more moles of gas. So the equilibrium will move to the left. Okay, it will favor the side with more moles of gas, the decrease in pressure. Okay, so we can say that the position of the equilibrium shifts to the left. Okay, shifts to the left. Okay, because a decrease in pressure. Okay, because a decrease in pressure favors the side with more moles of gas. So we can say because, okay, there are more moles of gas, okay, on the left. More moles of gas on the left. Hand side of the equilibrium. Figure 3.1 shows the two structural isomers of S2Cl2. Define the term structural isomer. Structural isomers are compounds with the same molecular formula, but different structures, okay, or different structural formula, but different structural formula. Suggest a value for the CLSS bond angle in isomer 1. Explain your answer. So the bond angle that we're looking at is the CLSS bond angle, which is this guy over here, CLSS. Okay, so we're looking at this bond angle. Okay, now sulfur is in group 16. Right? Same group as oxygen. So it has 6 valence electrons. Right? 2 of them are bonded. And then 4 of them are not bonded, right? So we have 2 lone pairs. Again, 6 valence electrons, 2 of them are bonded, and then we have 2 lone pairs. So this is very similar to what we have with water, right? The oxygen is making 2 single bonds, right? It's bonded to 2 atoms, and it has 2 lone pairs. So we can suggest that the bond angle will be the same. It might not actually be the same, okay, but based on our understanding of water, we can say that it will be 104.5 degrees. Now we have to explain this. Now for the explanation, okay, if we just had a tetrahedral structure, right, so if we just had 4 bonds, like we do for silicon, for example, right, then the bond angle is 109.5. Right, but here the bond angle is lesser than 109. It's going to be lesser than 109 because we have lone pairs present instead of bonds over here, and the lone pairs repel the bonds closer together. Okay, the lone pairs repel the bonds more than the bonds repel each other. Okay, so the bonds want to be further away from the lone pairs. Okay, so what we can say over here is that for the explanation, we can say that sulfur is bonded to 2 atoms and it has 2 lone pairs. Okay, it has 2 lone pairs, and we can say that the repulsion from the lone pairs is greater. The repulsion from the lone pairs is greater. Hence, the bond angle is less than 109 degrees. Draw a dot and cross diagram to show the bonding in isomer 2. Show outer shell electrons only. So for isomer 2, what we have is, okay, for isomer 2, we have this. We have this guy over here. So for this dot and cross diagram, we're going to start with the central sulfur, okay, the central sulfur atom. Now, sulfur has a total of 6 valence electrons. Now, this sulfur is making a double bond with another sulfur, and it's making 2 single bonds. That means 4 of its valence electrons are being shared, right, in these covalent bonds. Now, chlorine is in group 17, so it has 7 valence electrons. And makes a single bond with the sulfur and ends up having 8. So it's making a single bond here. And then we use the cross to represent the electrons of chlorine. Okay, so we have 1, 2, 3, 4, and then 5, 6. Okay, so that's 7 valence electrons of chlorine, and then 1 additional electron from the sulfur in this covalent bond. We have the exact same thing for the other chlorine as well, right? We have a single bond, so dot and cross. Then we're going to use cross for the electrons of the chlorine, right? So again, 7 valence electrons, and then that 1 electron from the sulfur, right? And then this sulfur is making a double bond with another sulfur, right? Making a double bond with another sulfur over here, right? Making a double bond with another sulfur, right? So here we have dot, cross, okay? And then sulfur has a total of 6 valence electrons. So if you look at the central sulfur, we're using dot for the electrons, right? We're using dot for the electrons over here. So we have 1, 2, 3, and then 4 from this sulfur. So we have 2 additional electrons, right? And then we're using a cross for this sulfur, so we have 2 over here, so that means we have 4 additional electrons. Okay, we have 4 additional electrons. Okay, and we're using cross over here, so we have 4 additional electrons. So we can clearly see over here that the central sulfur is exceeding the octet. It's not obeying the octet rule, right? It's not obeying the octet rule because here it initially had 6, now it has 10 valence electrons, okay, after bonding. So it can exceed the octet because it's in period 3, right? It's in period 3 and the third shell can hold more than 8 electrons. So here we have question number 4, which says organic compounds can be distinguished using chemical tests. Table 4.1 shows 4 pairs of compounds. Okay, so here we have a table showing 4 different pairs of compounds. Part A says, complete table 4.1 to identify a reagent that could distinguish between the compounds in each pair and give the positive result of the chemical test and identify which compound shows this result. Use a different reagent for each test. So for the first pair of compounds, A1 and A2, what's the reagent that we can use to distinguish between these two compounds? Now compound A1, right? Compound A1 over here is 1, 2, 3, and then 1, 2. It's a 5-carbon ester, right? It's a 5-carbon ester. Here we have the ester linkage over here, and this is ethyl propanoate. And then A2 is pentan 3-ol, right? It's a secondary alcohol. It's a secondary alcohol. So we want to distinguish between an ester and a secondary alcohol, right? The secondary alcohol can react with many different things. We can test for the OH group. Okay, we can use sodium. We can use sodium metal, right? And what we would observe is we would see bubbles of a colorless gas, right? Hydrogen gas would evolve. So we can say bubbles of a colorless gas. Okay. Bubbles of a colorless gas, right? That's hydrogen gas with compound A2. Okay, we have to identify the compound, right? That would give that result with. So that would be the positive test, right? We would see no bubbles with A1, right? Sodium metal is a test for the OH group, so any compound with an OH group. We can also use acidified manganate 7, right? We would see purple to colorless with A2 because the secondary alcohol will be oxidized to a ketone, right? We can use acidified dichromate 6, right? That's an oxidizing agent. Again, the secondary alcohol will oxidize to a ketone, and we're going to see a color change from orange to green. Okay, what about B1 and B2? B1 is butanone, okay? B1 is butanone, and B2 is methyl ethanoate. It's an ester again. So to distinguish between a ketone and an ester, right, we can use 2,4-DNPH, right, or 2,4-dinitrophenylhydrazine, right? That's a test for carbonyl compounds, and we would see an orange precipitate with the ketone, right? And there would be no result with the ester. Okay? Again, 2,4-DNPH can be used to test for aldehydes or ketones. Okay, so orange precipitate with compound B1. Another reagent that we can use is aqueous iodine. Okay, alkaline aqueous iodine, the iodoform reaction. Why? Because we have a CH3CO group, right, in this ketone. Remember, the iodoform reaction can be used to test for carbonyl compounds that have the CH3CO group or alcohols that have the CH3CHOH group. So over here, if we use alkaline aqueous iodine, we're going to see a yellow precipitate of triiodomethane. Okay. What about C1 and C2? How do we distinguish between these two? Here we can use aqueous bromine, right? We have a cycloalkane and we have an alkene, right? We have a cycloalkane, we have an alkene, and we know that alkenes undergo addition reactions with aqueous bromine, right? So we can use bromine aqueous. And the observation is that compound C2, the alkene, will decolorize aqueous bromine. Okay, so you can say decolorization. Okay, or brown to colorless or orange to colorless. Okay, decolorization of aqueous bromine. Okay, with compound C2. And then lastly, how do we distinguish between compounds D1 and D2? In D1, we have 3 OH groups, right? They're alcohols. We have 2 primary alcohol groups and a secondary alcohol group. And in D2, we have primary alcohol and we have a carboxylic acid group, carboxyl group, right? We have a carboxyl group here. Over here, we can't use something like sodium because it will react with all the OH groups, right? And plus, we can't really repeat the same tests, okay? We can't use the oxidizing agents either. We can't use acidified manganate 7 or acidified dichromate 6 because the primary alcohol group in D2 will react with the oxidizing agents. So we will see a color change, okay, with both of them. So we need something that will only react with the carboxylic acid, okay, and for that we can use sodium carbonate, okay, we can use sodium carbonate. Right, the acid reacts with sodium carbonate. It's an acid-base reaction, right? We get salt, carbon dioxide, and water. So what we see is we see bubbles or effervescence, right? We see bubbles or effervescence of a colorless gas. A colorless gas, okay, that will be carbon dioxide, okay, with compound D2. C1 has a melting point of negative 94 degrees Celsius and a boiling point of positive 49 degrees Celsius. Explain these properties by referring to the types of van der Waals forces between the molecules. The compound C1 over here is just a cycloalkane, right? Cyclopentane. Now, since C1 is a hydrocarbon, right? It's a cycloalkane, it's non-polar, right? So it has very weak intermolecular forces. It's non-polar, so it only has van der Waals forces due to instantaneous dipole induced dipole interactions, right? So we can say that C1, okay, we can say that C1 has a very low melting point and boiling point, okay, very low melting and boiling points, right, because it's non-polar. Since it's non-polar, right, non-polar, and the only intermolecular forces, right, intermolecular van der Waals forces, okay, or very weak intermolecular van der Waals forces due to ID-ID interactions are present, okay. Draw the structure of the cis isomer of C2, okay, the cis isomer of C2. So here in compound C2, they've given us the trans isomer, right? They've given us the structure of the trans isomer. We just have to draw the structure of the cis isomer over here. For the cis isomer, we're going to have this, and then instead of this alternating arrangement of the carbon chain across the double bond, right, the carbon chain will be on the same side like this, right? So 1, 2, 3, 4, and then 5, 6, right? 5, 6, right? So this is trans hex 2-ene, and then this is cis hex 2-ene. C2 forms a polymer when heated gently. Identify the type of polymer that forms from C2. Since we have an alkene over here, right, alkenes undergo addition polymerization. So the type of polymerization is addition polymerization. Okay, so we're going to get an addition polymer here. Draw one repeat unit of the polymer formed from C2. C2 was trans hex 2-ene. Okay, doesn't matter if it's trans or cis hex 2-ene, we get the same polymer, right? So this was C2, right? Trans hex 2-ene. Now, if we want to show the structure of the polymer, right, first we're going to draw the monomer in this form, right? We're going to arrange all the groups on the double bond above and below because it's the double bond that's polymerizing, right? So this carbon on the double bond is bonded to a hydrogen and a CH3, a hydrogen and a CH3, right? And then the other carbon over here, right, the other carbon over here is bonded to a hydrogen and a CH2, CH2, CH3. So we have a hydrogen and a CH2, CH2, CH3. Okay, it doesn't matter if we show it above or below. I've shown it in the sort of like the trans way, right, where the two hydrogens are opposite each other, but it doesn't matter if you show them on the same side as well because this bond will be rotatable. right, in the polymer. Because what happens in the polymer is that the pi bond breaks, right, the pi bond breaks, and then this guy can then bond to another monomer. Okay, this guy bonds to another monomer. So this is the structure of one repeat unit. Okay, the structure of one repeat unit. Okay, so these are the continuation bonds, and we only have two carbon atoms along the main chain for every repeat unit. Okay, because it's this double bond that's polymerizing. Again, it doesn't matter if you show the two hydrogens on the same side or on opposite sides, right? Because this bond can now be rotated. So here we have question number 5. Lactones are cyclic esters. Under suitable conditions, lactones form from molecules that have both an alcohol and a carboxylic acid functional group. Equation 1 shows an example of the formation of a lactone. Okay, so here this compound has a carboxylic acid group and an alcohol group. Okay, and we have self-esterification. So what happens here is that the oxygen from the alcohol, right, the oxygen from the alcohol ends up bonding to the C double bond O from the acid. So the oxygen from the alcohol ends up bonding to the C double bond O from the acid, and we get this cyclic ester. That cyclic ester is what we call a lactone. Figure 5.1 shows the synthesis of lactone P from compound M. M reacts with hot concentrated acidified KMnO4 to form N, C6H10O3 in reaction 1. Draw the structure of N. In reaction 1, we have the strong oxidation of alkenes, right? What happens is that the carbon-carbon double bond is ruptured. The carbon-carbon double bond is ruptured, right? And in this case, because we have a ring, what happens is that the double bond breaks and the ring opens up. But we get a single product. Okay, we get a single product over here, single organic product. It's a 6-carbon product, and we have a 6-carbon compound to begin with. Now, when we rupture the double bond, it's easier for us to identify the structure by numbering these carbons. Okay, so let's just say this is carbon number 1, and then 2, 3, 4, and then 5. Okay, so after we rupture this double bond, right, 1 and 5 are no longer bonded to each other. Okay, I'm going to say this methyl group over here is carbon number 6, right? After we rupture the double bond, these two are no longer bonded to each other. Now, what happens to carbon number 1? The way I've numbered it, okay, I've just numbered it for my own working, right? What happens to carbon number 1? It's a carbon that's bonded to two other carbon atoms. So what functional group does that become? So over here, this carbon, right, when this double bond ruptures, okay, we get a C double bond O over here, and we get a ketone. If the carbon on the double bond, right, this carbon here, the carbon on the double bond, okay, is bonded to two other carbon atoms, that becomes a ketone. Okay, so we can say that carbon 1 here, okay, carbon 1 over here becomes a ketone, right, C double bond O, right, and that carbon is bonded to a methyl group. Carbon is bonded to a methyl group, and then it's bonded to carbons 2, 3, 4, and then 5. So again, this is carbon number 1, the way I've numbered it. Okay, this is carbon number 6, that's the methyl group. That's the methyl group over here. And then this carbon over here is bonded to carbons 2, 3, 4, and then 5. So we have carbon number 1 is bonded to carbon 2, 3, 4, and then 5. This carbon 5 over here is a carbon on the double bond, right? The double bonded carbon that's bonded to one carbon and one hydrogen. It's bonded to one carbon and one hydrogen. So this carbon over here becomes a carboxylic acid, okay? It becomes a carboxyl group. So we get a C double bond O, and then the hydrogen over here that's not shown, the hydrogen becomes an OH. So we get CO2H, okay? So this is the way I've numbered it over here, right? 3, 4, and then 5. So again, carbon 1 becomes a ketone, right? Because it's bonded to two carbon atoms on the double bond. Whenever a carbon on a double bond is bonded to two carbon atoms additionally, right, that carbon becomes a ketone, okay, when we react it with hot concentrated acidified KMnO4. And then carbon 1 is bonded to 2, 2 is bonded to 3, 3 is bonded to 4, 4 is bonded to 5, and carbon 5, because it's a carbon with one hydrogen, it will become a carboxylic acid group. And then carbon number 6 is just the methyl group that's bonded to carbon 1. N is reduced by NaBH4, sodium borohydride, to form 5-hydroxyhexanoic acid in reaction 2. Construct an equation for reaction 2 using molecular formulae. In the equation, use H to represent one atom of hydrogen from the reducing agent. So if you look at reaction 2, in reaction 2, compound N, which is this compound here, is being reduced to form this compound. What we see over here is that the ketone over here, right, the ketone is being reduced to a secondary alcohol. Okay, the carboxylic acid is not being reduced. Okay, the carboxylic acid is not being reduced because NaBH4 is not a strong enough reducing agent to reduce the carboxylic acid. Okay, if we wanted to reduce both the ketone and the carboxylic acid, we have to use lithium aluminum hydride. Okay, LiAlH4. So we just have to write the equation for this reduction using molecular formulae. They've given us the molecular formula of compound N, right? C6H10O3, C6H10O3. And over here, the ketone is being reduced to a secondary alcohol. The ketone is being reduced to a secondary alcohol. So the CO is becoming a CHOH. CO is becoming a CHOH. So over here, we're just adding two hydrogens. So we have 2H, hydrogen from the reducing agent, and we get C6H12O3. Reaction 2 is a nucleophilic addition reaction. Suggest why reaction 2 creates a mixture of organic compounds. So this reduction, the mechanism for this reduction is a nucleophilic addition mechanism. The question is asking, why do we get two different compounds as our products? Now over here, okay, we have a nucleophilic addition reaction, okay, where the ketone is undergoing nucleophilic addition. Okay, the ketone is undergoing nucleophilic addition to form the secondary alcohol. Okay, and the product over here is a chiral center. The product has a chiral center, right? This carbon is bonded to a methyl, an OH, this entire group, and a hydrogen that's not shown. So it's bonded to four different atoms or groups of atoms. And the reason we get optical isomers here is because the nucleophile, okay, can attack the trigonal planar carbon from either side. Okay, so for example, if I drew the ketone carbon this way, then the nucleophile, okay, the nucleophile can attack this carbon atom from the front or the back. Okay, it can attack this carbon atom from the front or the back. Okay, so that's why we end up getting a mixture of optical isomers. So what we can say over here is that the trigonal planar carbon, right? That's the ketone carbon, can be attacked from either side. It can be attacked by the nucleophile, from either side, resulting in the formation of a mixture of optical isomers. Draw lactone P, the product of reaction 3. Okay, so when we talk about reaction 3, right, in reaction 3 we're getting a lactone, so 5-hydroxyhexanoic acid is undergoing self-esterification to form a lactone. Okay, so we're going to keep this here. Again, remember, in esterification, what happens is that the oxygen from the alcohol, from the OH, bonds to the C double bond O from the acid. Okay, the oxygen from the alcohol bonds to the C double bond O from the acid. Okay, and we end up getting an ester. So what happens here is, okay, we're going to start with the C double bond O over here. I'm going to start with the C double bond O, right? And this carbon over here bonds to the oxygen from the alcohol. This carbon bonds to the oxygen from the alcohol, right? What ends up happening over here is that this oxygen bonds to this carbon. Now this C double bond O carbon, I'm going to call that carbon 1, is bonded to carbon 2, right? That carbon is bonded to carbon 3, Carbon 3 is bonded to carbon 4, and carbon 5 has the OH group, right? Carbon 5 over here has the OH group. So carbon 1 is bonded to carbon 2, right? I'll call this carbon 1 is bonded to carbon 2, and then carbon 2 is bonded to carbon 3. Carbon 2 is bonded to carbon 3. Carbon 3 is bonded to carbon 4. Carbon 4, and then carbon 4 is bonded to carbon 5. Okay, and then carbon 5 is bonded to the oxygen. Carbon number 5 is bonded to the oxygen. So again, carbon 1 is bonded to carbon 2, carbon 2 is bonded to 3, 3 is bonded to 4, 4 is bonded to 5, and then 5 is bonded to the oxygen, and that oxygen ends up bonded to the C double bond O. And we see over here carbon 5 is also bonded to carbon number 6, which is just a methyl group, okay, in this ring. So what we get over here is this, okay. We have a methyl group on carbon number 5. Okay, so this is the structure of the compound. So let me draw this a bit nicer, right? This is what we get. So this is what we get. So this is our compound. A student monitors the progress of reaction 2 using infrared spectroscopy. Use table 5.1 to suggest why it is difficult to distinguish between N and 5-hydroxyhexanoic acid using infrared spectroscopy. So if we look at compound N and 5-hydroxyhexanoic acid, right, we look at compound N and we look at 5-hydroxyhexanoic acid, right? Are there any bonds that we can use to differentiate between the two of them? Now, if you notice, both compounds have a C double bond O, right? Because both compounds have a carboxyl group. Both compounds have a carboxyl group, and both compounds also have an OH bond, right? This guy over here has a carboxyl or carboxylic acid, right? And this guy over here has a carboxyl and a hydroxyl group. But this peak won't be observable because it's going to overlap with the very broad OH absorption due to the OH from the carboxylic acid. So there's no bonds in these two compounds that are different from each other that we can use to distinguish between the two compounds. Okay, so that's why it's difficult to monitor the reaction using infrared spectroscopy. Okay, because infrared spectroscopy is used to identify the presence of specific bonds. Okay, so over here we can say that both compounds have CO and OH bonds. Therefore the peaks or absorptions, right, the absorptions will overlap. Okay, and we will not be able to distinguish between these two compounds. Unknown lactone Q is analyzed using mass spectrometry. Table 5.2 shows information from the mass spectrum. Use these data to deduce the structure of compound Q. Show your working. So they've given us information about the M or the M plus peak and the M plus 1 peak. We've been given the abundances for these two peaks, right? The M or the M plus peak is because of the molecular ion with carbon 12s, and then the M plus 1 peak is when we have 1 carbon 13. We can use the relative abundances of the M and the M plus 1 peak to find the number of carbon atoms in a molecule, right? We know that the ratio of the M and the M plus 1 peak, or we can say the M plus 1 and the M peak, is equal to 1.1 N divided by 100, where N is the number of carbon atoms, right? So over here, the relative abundance of the M plus 1 peak is 3.15, right? 3.15. The relative abundance of the M or the M plus peak over here is 95.5. Okay, and this is equal to 1.1 N. Again, N is the number of carbon atoms divided by 100. So we can solve for N. And over here we get N is equal to 3. That means that this compound over here has 3 carbon atoms. Okay, it has 3 carbon atoms. Okay, so we have a 3 carbon lactone. Now in a lactone, we have this ester group and we have a cyclic ester, and we just have 3 carbon atoms. So I've shown 1 carbon atom here, and we have a cyclic ester, so we only have 2 more we only have 2 more carbon atoms. So we have 1 and then 2 and then 3 carbon atoms. We have a 3 carbon lactone, 1, 2, 3, right? That's 3 carbon atoms. And we have this cyclic ester. Okay, so this is our lactone over here. And we can double check the MR, right? We have 3 carbon atoms, so that would be 12 times 3, that's 36. We have 2 plus 2, 4 hydrogens, so that's 40, the mass, and then we have 2 oxygens, so that's 40 plus 32, which will give us a mass of 72, an MR of 72. So that's our answer. Okay, that is the structure of lactone.